So today we are going to talk about descriptive statistics. So you should launch your RStudio app, and then we go together and open a new script. And we do that by using the menu, File, New File, R script. Right? So what we do now is to clean the workspace. This is a new class, so we need a clean workspace. We don't need objects. R loads the objects created in the previous lesson. So we might have some objects in our workspace. We do not need them, therefore we erase them. And the command to erase everything is this one here. That remove the list containing the whole workspace. So I can comment this command here. I'll write a fence and then write cleaning the workspace. And you see that the color changes. That means that we are writing a command which is not executed. So you see I wrote the command, but I did not send it to the console. So before we execute the command, we need to send it to the console by pressing Ctrl-Enter, or in my case, I have a Mac, it's Command-Enter. Here we go. The environment, the workspace is empty now, and that's good for us. Second step, we save the script. I'll save it in a folder of my choice. Do whatever you please. I mean, put it somewhere where you can find it. I'll put it here. So today it's 2020, 10, then it's 6, if I remember well. So now this script is saved into a particular folder of our choice. So what we have to do now is to set the working directory. Where do we set it? We set it to the same folder where we have saved the script. And we use the menu, session, set working directory to source file location, right? So let me summarize the 3 steps. Step 1 is to clean the workspace. Step 2 is save the script in a folder of our choice. Then, third step, set the working directory, right? So these are the 3 steps we need to learn and do them at the beginning of every R session, right? So what we have now is a data set I mean, we have organized an experiment. The experiment must be valid, and we know that every valid experiment has replicates. So we had a family of data. The first step is to describe those data. I mean, we might have, let's say, 1,000 data, 10,000 data, 100 data. I mean, we cannot report all the data. So we have to find some statistics to describe the properties of the data set, right? And there are basically three properties that we want to describe. And the three properties are listed there. So we have the location of the dataset, we have the spread of the dataset, and we have the shape of the dataset. We will not talk about the shape because that's not really very often described. So we will only talk about location and spread. The meaning is, I think clear. So location means where do the datasets stand in the axis of real numbers? We are talking about quantitative data. A quantity. Let's say height, yield, concentration, basically whatever you want, but it must be a quantity. We already talked about quantitative data. They are different from categorical data or count data or rates. These are quantities. And we can describe the location. Where are the data located? And the second property is the spread. How spread are the data? They can be located in a very narrow space along the real axis, or they can be located in a very large space. So they are very spread, right? And we have statistical indicators to describe these properties. So the first statistical indicator to describe the location, and you should know it, is the mean. So let's do one thing. We will use some data I have in an external repository. So what I'm doing here is writing the name of the repository. The repository is named, it is on an online repository. We could do something like this, which is handier. So I show you. So I'm writing a few character strings. The first string at line 6 is named file path. And you see it's something like an internet address, https www.casaonofre.it/_datasets. I think the best I can do is to pass you these two comments over the chatbot so that you don't make mistakes. So this is the first string, and it expresses the file path. So the place where the file is located. The second string at line 7, it's file name, and the name is heights.csv. Right? So now we have to join these two strings. So files, we use the function paste it joins the two strings, file path and file name. You see, I have used two arguments to this function here. The first argument is the path to the file. The second argument is the name of the file. They are joined by using no separator. So they are just put one after the other without any separator. Look at me. I send the first string. I'm sending the second one. And then I'm creating a new string that is the connection of the two strings. So this is file. You see? Hope the mechanism is clear. So we are creating the file name by joining two strings. The file name is rather complex, so we need to join two strings, but we can also have just one string for everything we need. Then we read this file by using the read csv command. Oh gosh. Looks as if it doesn't work. Let me see why. Okay, yeah. So I made a mistake here. Right, so look at the function at line 10. We are assigning to a variable named dataset. What do we assign? We assign the file. We ask R to read the file, which we have given him as a string of characters. And we need an extra argument that is header. Header means that the first row of the file contains the names for variables. So this is a real data frame. Look, it is a data frame with three variables. The first variable is the ID. There are 20 observations. These are heights taken on plants of different genotypes, varieties, right? Am I going too fast or too slow or whatever? Is that okay? What about home? Can you feel me? Okay. So here we go. Now we have a new data set, a new data frame loaded in memory containing heights. Let's assume that you want to describe the location by using the mean. This would be the mean. It's 164. That's very easy. We use the function min, and we pass the data set. Just look at me here at line 14. I cannot write simply mean height, because height is not existing on the workspace, because it is hidden inside a data frame. So we need to tell R where it can find this vector we want to use, the vector height. And we do that by using the extractor. So dataset $height. So that's it. So I made a mistake here. Dataset $height. Now I get the mean. And I guess you know what the mean is. It is the sum of the data divided by the number of the data. So you You must know this. This is a good measure of central tendency, but it is not the only one. The second measure is the median. What is the median? The median is the central value. It's a value so that 50% of the data are higher and 50% of the data are lower. So it's exactly in the middle. It is pretty easy to calculate it. We take the data, right, and we sort them. That's pretty easy. You see, I'm sorting the data in increasing order. So now we see that the data go from 141 to 191. We have 20 data. The number of data is even, so we do not have a central datum. So we have to take the two central data, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11, and we calculate the mean. But it is easier if you do like this, median, data set, and height. So that is exactly what we expected. Right? So the median is the central value in a distribution. If I have an odd number of values, I take the one in the middle. If I have an even number of values, I have to take the two in the middle and average them. Right? So it is important to say what are the properties of the median. We say that the median is more robust. So the mean is important, but the median is more robust. What do we mean by using the word robust? I'm talking about outliers. Do you know what outliers are? Outliers are strange data. Strange in the sense that they are very high or very low compared to the data set. You know, let me tell you. Just imagine that we have a data set. We call it Y, and I'll use this. I'll make a vector, and I'll write 10, 12, 13, 14, 16. So a very normal data set. So the mean for this data set is simply 13. The median is 13. So they are equal. Now let's try to see what happens if we have an outlier. Here, instead of having 16, I have 160. This would be an outlier because it's a very high value, which is really high compared to the other ones. So what is the mean now? The mean has increased a lot. Oh, sorry. But I have to execute the command before. So the mean is much higher now. From 13, it rises to 41.8. Yes, because the outlier is impacting a lot on the mean. But what about the median? The median doesn't change. Because always the central value, regardless of outliers, That's why we say that the median is robust. We see that the median is not affected by outliers. It is robust. And that's important. It's an important property when we describe central tendency. Because if we want to describe central tendency for values, for data sets containing a few outliers, then we have to use the median. Otherwise, the mean is strongly influenced by those outliers. Good. Sorry, I made a mistake here. Any question about this? I'd like to start talking about measures of spread. So, what is my aim here? Measures of spread. So we need to understand how spread are the data along the real numbers line. Well, I could have this vector here, 100, 101, 102, or perhaps 99, 100, and 101. And I could have this one here. See, 1, 100, and 199. So these are two small groups with the same mean. You see that mean y is 100 and mean y1 is the same, 100. But you see that these two small groups are different because the first one has a very small spread and the second one has a very big spread. So describing the mean, or better, describing the central tendency of a data set is not enough. We also need to describe the spread. Okay? And how do we describe the spread? We have several possibilities. The first one, use the range. What does this mean? Using the range means taking the higher and the lower value. So I can get these values like this. Mean stands for minimum. Let's use the original data set. Data set and 8. And we can use the maximum. So now we know that the data go from 141 and 191. So we know what the basic spread is. Well, this is really not sufficient because we might have outliers. And if we have outliers, the range is strongly affected. So it can show that the data set is much more spread than it is indeed. So we need to use other measures. One possibility is to use the percentiles. So what are the percentiles? I can give you a definition. We can read it together. They are the values below which, here you go, that's the definition, the values below which a given percentage of observations falls. So the 25th percentile is the value below which 25% of the observation may be found. So I could use, for example, the 25th and the 75th percentile. So because I have two numbers, the first one is higher than 25% of observation. So it is below the mean. And the 75th percentile is the value below which we have 75% of observations. So it is above the mean. And if you think about this for a while, look at this. There must be a graph here. No, doesn't matter. If you think about the data, let us calculate the percentiles. The median is 1 percentile. I mean, the median is the 50th percentile, right? So, and we can use the function quantile. I take data set and height and use the argument probes and pass in a vector of probabilities. So I want the 25th percentile, the 50th percentile, and the 75th percentile. And here we go. So let's think about these percentiles here. So the first value is 152.75, and this is the 25th percentile. We mean that 25% of values are lower, right? Then at the right, we have the 75th percentile, 174.25. What does this mean? It means that 75% of values are lower. That also means that 25% of values are higher, right? So 25% values are lower than 152.75, and 75% values are lower than, made a mistake here, 174.25. That means that 50% of values are inside the interval 152.75 and 174.25. So that's the meaning of the 25th and the 75th percentile. They can be used because we know that 50% of values are included in that interval. Okay? So it's 9:30. I propose that we make a short stop, 10 minutes, so that I can check that everything is right here. And you can also check that everything is right in your script pane. And then if there is something wrong, you just ask me and stop me so that we can go ahead together. Is that okay? The first one is the so-called deviance. Deviance, or sum of squares. So what is that? Let's take the height. So I show you the data here. If we take the heights and subtract the mean, so what's happening here? These are distances from each one datum, each one value, and the mean. So for example, the first value is 8 units above the mean. The second value is 10 units below the mean, right? So these are the distances from the mean. Of course, if the distances are high, the spread is high. If the distances are small, the spread is small. But I cannot sum the distances because the sum is 0. The mean is the central value. So it's the value so that the sum of the distances are 0. So the mean is built to respect the assumption that the sum of distances is 0. So I cannot sum distances. But I can square them and sum the squares. So I can sum the squared distances from the mean. That is the sum of squares. So I do like this. Put the brackets around, then square, and then again sum. So this would be the depth 4050. I call it as so this is a good measure of spread because it is high when the spread is high and it is small when the data are very close to one another. And this is a measure of spread which you should learn because we will use it very often in the future. Now, two things are important. First, the heights here are measured in centimeters. So what is the measurement unit for the deviance? First aspect about the deviance, which we do not like much, which we may not like much, the measurement unit is squared. And this is the first problem about the deviance. And the second problem about the deviance, too, is that, of course, if we have two data sets with a different number of individuals, well, when we have a high number of individuals, the deviance is high. And when we have a low number of individuals, the deviance may be low, just because we have a lower number of values to sum up, a lower number of squares. So we should never use the deviance to compare the spread of two data sets with different numerosity. Right? So what do? We take another a spread, which is very often used, that is the variance. Variance or mean square. Right? So we take the sum of square and divide by the number of data, length, data set, and height, minus 1. Oops. So, of course, there is a shortest way. That is simply use the function var. Right, so it's, you see it is the same. And of course you will prefer the command at line 49. So now we have, of course, we have now solved the problem of numerosity. As we divide by the number of individuals minus 1, if I have a big data set, then I divide by a high number. If I have a small data set, I divide by a low number so that the spread are comparables. The spreads are comparable, right? But we still have the problem with the measurement unit because we are still on a squared scale. So the measurement unit is still squared. So what do? We take the so-called standard deviation. That's the square root of the variance. So if I call the variance mean square, ms, then the standard deviation is the square root sqrt mean square. And of course, I have a shortcut here because I can use the function sd. See, it is totally the same. Now we have solved both our problems. Because we have now a measure of a spread, which we can use to compare samples, populations or samples or data sets characterized by a different number of values. And the measurement unit is in centimeters, which is okay, which is what we wanted. So, how do we describe the data? Our way to describe the data is something like this: mean and standard deviation. All the other measures are important, but to describe the data, location and spread, what we normally do is use the mean and standard deviation. So do not forget this. We should never present the mean alone. We should always present mean plus standard deviation, because we need to give an idea about the location of the data set and about its spread. Otherwise, information is not complete. There is another measure of spread which is very often used. I mean, if I tell you I have a data set with a standard deviation of 1, and you would probably tell me, is it big or is it low? We do not know until we see the mean, because if the mean is 100 and the standard deviation is 1, that means that the spread is small. But if the mean is 1 and the standard deviation is 1, the spread is high. Ciao, direttore. Okay? So, there is another measure we can use to have an idea about the variability of a data set without considering the mean. That is called the coefficient of variation. All right? So here, use and standard deviation to describe a group of data. And the coefficient of variation is the ratio between the mean and the standard deviation. So the other way around. We have the standard deviation at the numerator and the mean at the denominator. So I take the mean, I take the standard deviation, I divide by the mean, and sometimes, rather often, I multiply by 100. So what I see is that in this data set, we have 8.9% coefficient of variation. So it says a lot here. And for example, when you buy chemical instruments, the variability of the instrument is measured by using the coefficient of variation. So this is the coefficient of variation. It's very important to know it. Most often use mean and standard deviation. We will use the coefficient of variation only when we have to describe the variability regardless of the mean for chemical instruments or for measurement instruments. We usually have different groups. We do not have only one group of data. We have different groups because we have different treatments. Also in this case, we have different treatments. If we look at the data set describing different groups, let's look at the data set. I'll use this function here, head data set. It shows the first 6 lines of a data set. It is very important because I just can get an idea about the data set. And you see that we have different groups. We have different genotypes. So we have measured the height for plants belonging to different genotypes. If I want to describe the groups, then I have to find a way to apply the mean, to calculate the mean for each group. This is my problem now. How do I calculate the mean for each group? There is a function which is the very basic function for doing this task, and it's the function tapply. There are much more advanced functions in R to do this task, but we will use the basic one. We start with that. So the function is tapply. So it calculates statistics by group, and it needs 3 arguments. The first argument, the variable, which we want to calculate the mean of, or the statistic of, and this is height. Second argument, the variable coding for the groups. This variable must say which group belongs each observation. And in this case, it's data set and var. Then, third argument, we need to say which statistic we want to calculate. And in our case, we want to calculate the mean. Here, what we get, we have 4 groups, 4 genotypes, C, N, S, V, and we have the means for the groups. So I write mu. Well, this is the Greek letter, and it should be me, but I'm very used to saying mu. So I will say mu, even though if you are from Greece, you would probably tell me that the best pronunciation is me, not mu. But never mind. It is often used for statistics, and mu is used for the mean in every statistical books. So I'm creating a variable called mu. Mu contains the means for the groups. Now I'd like to calculate the standard deviation, because I said we should never present only the mean. We should always present mean and standard deviation. So I will calculate the standard deviation. I'm copying the comments and replacing mu with sigma, another Greek letter which we use for the standard deviation, and replace the function mean with the function SD, that stands for standard deviation. So now we can cbind. In order to create a data frame with the means, we simply cbind df, we cbind mu and sigma. We can do this. It is a matrix, but we use it as a data frame. So now we have a descriptive data frame, which gives us the means and the standard deviations for each group, which is useful. I'm adding you this final part. We are always in this situation. We have an experiment, we have different groups, we need to describe the groups, and one possibility, the most common one, is to use mean and standard deviations for the group, for each group. And that's the code to one possible piece of code to obtain such descriptive statistics. Of course, we have countless ways of doing the same thing, but this is the basic one, and I would like you to learn it. So, now, once we have described the observation, what we can do is simply plot the observation. For example, by making a bar plot. Now, that's pretty easy. I copy the code to be faster. Well, just let me copy the first, and then we'll see what happens. So, now, I need to make it slightly bit. All right, so I'll pass you the function, and then we'll discuss it. So you see that the function is bar plot. We are making a bar plot indeed. So what do we have to plot? We have to plot df $mu. So we are taking the column that contains the mean, and that will be used to for the heights of bars, right? Then I would like to know what it has to write below each bar. And so we take the names of the group, but we don't have the names here available. So we can use, we have a function that is row names df, right? So it says the row names are the names of the genotypes which we want to write below each part. So we write name sarg is equal to the names of the rows in df. So first argument, the mean. Second argument, the names to write below each bar, which are taken from the names of the rows in the original matrix. Then we write the range for the y-axis, which goes from 0 to 200. And then the label for the y-axis. Right? Now I have to enlarge this part here, run the command, and I have one problem here. Let me see what it is. Oh gosh, I didn't run this. df and move. But this is strange because it doesn't like that I have used move and df perhaps. So I'll change the name. I'll explain you in a while. Let's start. Okay, and let's see what the problem is. Start and move. All right, yes. I need to add, sorry. Data frame. I wanted to use a shortcut, but it is probably not possible to use it this way. All right, now it's much better. You see, I made a mistake because I told you I was creating a matrix, and matrices, the columns of matrix cannot be accessed by using the $sign. So we have to transform the matrix into a data frame. And we use a transformation function here. So we could do something like this. df, so that was not the problem. df is the data frame obtaining from the matrix, which was obtained by C binding, move, and sigma. You see, I'm making a transformation. So this would be the correct coding. I'm using two functions, one inside the other. The external function is a transformation function. The internal function creates a matrix. Right? Now I still have row names, which are okay, which I can use to retrieve the name arg. And then I use everything here. Oops, sorry. So this would be df and move. Oh gosh, again. Now it should be okay. Okay. So I'm giving you the code, the clean code to plot the bar plot. Shall we go through again? First, we have used the tapply function to calculate the mean and the standard deviation. Then we C-bound the mean and the standard deviation and transformed the table, that was a matrix, we transformed the matrix into a data frame. Then we used the bar plot function to plot the mean, and below each bar, we put the names of the rows in the data frame. But then we have a problem here, because we don't have the standard deviations. Standard deviations are usually plotted by using bars, vertical lines, small vertical lines. You've probably seen it in scientific publications or whatever. I'm copying the code, although this is not good because I make mistakes when I copy the code. It would be better to write it from the scratch, but never mind. So we go. Now, it's rather complex, and I want to show you that easily. Now, look at here. Look, I'm making the graph a bit smaller. So, we have used the function barplot to assign a variable which we called coord. That stands for coordinate. What is coord? Let me explore it. Coord. These are the x-coordinates, the abscissas of the bars, right? So this is the central abscissa of each bar. It is clear that if we want to draw lines for standard deviations, we have to put them in the center of each bar. So we can use these coordinates here. And next we use the function arrows. Arrows draws arrows in a graph. Where do we want to draw these arrows? So we want to use the coordinates, coord, as the x coordinate, right? So we use syntax is like this. We have to put arrows x0, meaning the coordinates of the abscissa for the starting point, and y0, that is the y coordinate for the starting point. Then we have the x coordinate for the arrival point, and the y coordinate for the arrival point. So in our case, the x coordinate for the starting point is coord, the center of each bar. Then we have the y coordinate for the starting point, that is the mean minus the standard deviation. So I have to correct here because I have used df here. So it's mu minus sigma, right? Then the arrival point, the arrow must be vertical. So the x for the arrival point is the same as for the starting point. What changes is the y coordinate, because we have to put df mu, that is the mean, plus df sigma, right? So I have four coordinates: starting coordinates x and y, and the arrival coordinates x and y. Then I have some other arguments. This is the length of the arrow, the length of the external, the final, initial and final points, the angle of the arrow, which is 90, and the chord for the arrow. Chord equal 3 means that we want to draw the arrow head at the beginning and at the end. So what comes out is this. And that is exactly what we are looking for. So I'm passing you the whole code to draw. Let me clean it. All right. So this is something you should learn because it's very handy. And please pay attention to the way we report results. We report results always by using the mean, which might be a bar, which might be a point, which might be a symbol, what you would like, but we always report the standard deviation along with the mean. Please note that in this case, we have twice the standard deviation because we have plus standard deviation and minus standard deviation. So it's twice the standard deviation. And that's okay. That's normal. That's what we do usually. And in a few weeks, I will tell you the exact meaning of this. So I'm happy with this. Any questions? Yeah, another thing I'd like to show you. Any questions? I have Claudia here. She has no questions. Kang, no questions. What about the other ones? Is it clear? Small feedback, please. Yeah. Good. I want to show you another type of graph, which is very used and handy. Perhaps it is not really useful in this setting here. We have just a few data for each group. We use this type of graph when we have 20 data or more, but in the book, I have shown an example with 20 data. In this case, well, I'll do that with our data set. It's something like this: box, plot, data set. Now we can do something different, I guess, here. So just put height against groups against row names df. Let me see whether this works. No, doesn't work. So I have to write data sets. Yeah. And that is not right because I need to put here head data sets. So it's var. Okay, now it's okay. So now we have the graph and we have the code, and I have to explain the code to you. So there are a few problems, and we'll find some workarounds. The name of the function is the box plot. What we are drawing now is the box whisker plot. Box whiskers plot. It's box and whiskers, right? We use the function to tell R what it should draw. The function is this. Height, look at the tilde. Tilde means is a function of. So you will not find the tilde in your computer. It's rather hard to type it because we need to use the ASCII code, which is not immediate. So I'm passing you the symbol over the chatbot so that you can copy and paste, and that's more handy. It is important because we express one variable as a function of the other one. The tilde means is a function of. So what we are telling are, please plot, make a box whiskers plot by using the height as a function of the genotype, which is coded as var. Look, the second thing to pay attention to is that we used height and var without the dollar sign. So we are not telling R where these two vectors are located. But note that I have used the further argument, which is data, and I told R, look for the variables inside the data set. So this is another way of expressing where the vectors are. So I could have as well have written something like this. Data set $height, data set $var. So these two commands are totally the same, but the first one is clearer. But they are totally the same. So, and what does the box plot means? I'm making it slightly bigger. You see that we have boxes and whiskers. You see? So what is the box? The box goes from the 25th to the 75th percentile. So this gives us the spread of the data set. For each group, this bar here at the center, not the center, but in the middle of each box is the median. So you see that the median is not central with respect to the 25th and the 75th percentile. That's normal because we have more data in one small range than in the other one. And what are the whiskers? The whiskers show the minimum and the maximum value for each group. So you see that this box plot gives us a lot of information because it says what is the minimum, what is the maximum, what is the 25th percentile, and what is the 75th percentile, and the median for each group. So we have full information about the location and about the spread, and this is telling us something about the shape also. We didn't talk about the shape, but it is telling us, for example, that the 25th and 75th percentile are closer to the maximum value than to the lower value. So this population is not symmetric. But we didn't talk about the shape, and it doesn't matter. But this graph gives us full information. So, I guess it's enough, isn't it? I gave you a lot of information for today. And you are still at the beginning. You have to go to the end of the day without exploding. So 10:26, I think we might stop it here and go ahead tomorrow.